How do factories keep Nerds, Oreos, and Snickers tasting identical at full speed? Each one has a hidden secret where their missing ingredient can ruin the product. In this video, we follow the process from syrup cooking and baking lines to layering and high-speed wrapping, revealing the critical checkpoints that lock in texture every time. Nerds begin as a hot, clear sugar melt that is deliberately forced into a brittle glass because the final candy is defined by controlled fracture rather than molding. The line starts by preparing a sugar solution that can be concentrated without seeding unwanted crystals. Granulated sugar is screened to remove clumps and to tighten the crystal size range. Fines are limited because they dissolve too fast and can caramelize at hot surfaces. Water is filtered and tempered so dissolution conditions stay repeatable. Corn syrup is held in jacketed tanks to keep viscosity stable for metering. Acid powders, salts, flavors, and colors are staged in separate feeders because Nerds often run multiple flavors in parallel. Sugar and water enter a dissolver with strong agitation. The goal is a fully dissolved solution with no grain residue. Any undissolved grain becomes a nucleation site that can trigger premature crystallization. The solution passes through strainers to remove stray solids and then feeds a continuous cooker. In the cooker, the syrup is heated rapidly to drive off water and raise solids to the level needed for a hard candy glass. Many systems heat under pressure so temperature can rise above the normal boiling point without flashing. That allows fast heat transfer and short residence time. The syrup then enters a flash stage where pressure drops and water vapor leaves quickly. Flashing tightens final moisture and also cools the syrup slightly by evaporative loss. Final solids must land in a narrow window. Too wet and the sheet will bend and tear instead of shattering. Too dry and the sheet will explode into excessive dust when fractured. Corn syrup is injected as a crystallization control lever. It reduces uncontrolled graining and helps keep the candy glass consistent from run to run. Its metering is precise because it also changes brittleness and fracture behavior. After the final concentration step, the syrup is cooled through heat exchangers to a temperature that protects flavors and supports controlled casting viscosity. The process often splits into two streams at this stage to create two flavors and two colors for the paired pack format. Each stream receives its own acid and flavor additions. Acid is added after the hottest zones because high temperature and low pH accelerate sucrose inversion and can change texture. The acid is usually dosed as a solution to ensure fast dispersion. pH is controlled because it influences sourness and also influences how hygroscopic the finished candy will be. Flavors are injected late and mixed rapidly. Oil-based flavors are emulsified or carried so they will disperse evenly. Color solutions are filtered and then metered into each stream. Uniform color matters because Nerds are small and translucent and any streaking is visible. Static mixers fold the flow repeatedly to eliminate bands before casting. Casting turns the hot syrup into a thin sheet that can be fractured into granules. The syrup is deposited onto a cooled steel belt or onto trays as a continuous ribbon. Deposit rate and belt speed set thickness. Thickness is a key variable because it determines cooling rate and fracture size distribution. A thicker sheet cools slower and can retain internal stress. A thinner sheet cools fast and can become too brittle at the surface. Cooling is engineered to produce an amorphous glass with minimal crystal growth. Cooling plates under the belt pull heat out evenly. Air above the sheet is controlled so humidity does not condense and so surface remains clean. Rapid cooling locks the syrup into a glassy state. If cooling is too slow, crystals can grow and the candy becomes gritty rather than sharp and crunchy. As the sheet cools, it can be conditioned to create predictable fracture behavior. Some lines flex the sheet slightly over rollers to introduce controlled microstresses. Others lightly score the surface to create preferred break paths. The aim is to reduce random oversized chunks and reduce the need for aggressive crushing later. The sheet must reach a brittleness that breaks cleanly under compression rather than smearing. Once the sheet is brittle, it is released from the belt and fed into a primary breaker. The primary breaker uses toothed rollers or oscillating bars to crack the sheet into chips. This first break is staged to avoid shattering into dust. Chips then feed a secondary reduction stage, often roll crushers, that bring pieces down toward the final nerd size range. Roll crushers are used because they apply compressive force and yield angular fragments rather than rounded beads. Crusher gap is the main size control. A smaller gap yields more fines and a narrower top size. A larger gap yields more oversize that must be recirculated. Feed rate must be steady because surges cause inconsistent reduction and more dust. Roll speed and surface texture also matter because they control how the chip is gripped and fractured. The goal is irregular pieces with sharp facets but limited powder. After crushing the material enters screening. Vibratory screen decks separate by size in multiple fractions. The target fraction continues as product. Oversize is returned to the crusher for another pass. Fines are removed because they clump easily and create dusty packs. Fines can be used as controlled recycle seed in some systems, but only in small ratios because they raise cohesion and reduce free flow. Because nerds often come in two distinct colors, each stream is processed separately through crushing and screening. This keeps recycle loops color pure and prevents shade drift. It also allows each stream to be tuned for its own brittleness because acid and flavor loads can shift glass strength. If one flavor tends to shatter more, the crusher gap can be opened slightly for that stream while keeping the other tighter. Conditioning follows sizing. Even though the candy is glassy, it can hold slight moisture gradients from casting and cooling. Conditioning allows moisture to equalize inside each granule. This stabilizes crunch and reduces caking risk. Conditioning bins use controlled dry air so the product does not absorb humidity. Humidity control is critical because hard candy surfaces can become tacky when water activity rises. Tack leads to clumping and also to color transfer between pieces. A light finishing step can be applied to improve flow. Anti-caking agents can be dusted at very low levels in a tumbler. The purpose is to reduce surface adhesion points and to improve hopper flow. Application must be uniform because local over-application changes mouthfeel and creates visible dust. After tumbling, the product can be aspirated lightly to remove excess loose powder. For versions that emphasize a stronger sour burst, some sourness can be placed at the surface rather than only in the body. This is done by misting a very small amount of binder and then applying an acid-sugar blend. The binder must be extremely light so it does not dissolve the glass surface. The acid blend adheres, and then the product is dried quickly to set. This creates a fast sour hit at the tongue because surface acids dissolve first. If the product format requires blending the two flavors, blending is performed after each stream has been sized and conditioned. Gravimetric feeders meter each color stream into a blender at the target ratio. The blender uses gentle paddles so it mixes without grinding. Over-mixing would generate fines by abrasion. The blending time is therefore short, and the geometry is chosen to fold the streams rather than shear them. Before packaging, the blended product is screened again to remove any fragments created in blending and conveying. This final screen improves pack cleanliness and improves weigher accuracy. Metal detection can be placed at this stage because product flow is stable and pieces are dry. Packaging begins with controlled feeding into weighers. Multi-head weighers are common because they can combine multiple small hopper dumps to reach target weight quickly. Consistent flow into the weigher depends on low fines and low humidity. Hopper walls are steep and surfaces are low friction. Vibration is used sparingly because vibration can create abrasion dust. For bag formats, the weighed portion drops into a vertical form fill-seal machine. Film is formed into a tube and sealed longitudinally. The portion drops through a funnel and settles. Transverse seals close the bag above and below the portion. Seal timing must keep granules away from the seal jaws. Dust management is important because sugar dust in the seal area can weaken the seal. Oreos are manufactured by producing a cocoa cookie wafer with a controlled snap and surface texture, producing a fat-based creme that holds shape without refrigeration, then assembling 2 wafers around a measured cream deposit before packaging to protect crispness. The cookie wafer begins with flour and cocoa handling because particle size and moisture define dough behavior. Flour is sieved to remove lumps and to aerate it for consistent hydration. Cocoa powder is sifted because it compacts and forms clods that create dark streaks. Sugar is screened to control crystal size and reduce dust. Leavening and salt are weighed precisely because they drive spread and porosity. Fats are tempered to a plastic consistency so they cream evenly and do not separate during mixing. Water is tempered because dough temperature controls sheeting and bake spread. Mixing starts by building a fat-sugar phase that controls texture. Fat and sugar enter a mixer and are creamed until sugar. Crystals are uniformly wetted and small air cells are incorporated. Air incorporation is controlled because it influences wafer porosity and snap. Too much air yields fragile wafers that crumble during sandwiching. Too little air yields dense wafers that lack the intended crisp bite. Salt and leavening can be added during creaming so they disperse evenly through the fat phase. Water is introduced next in a controlled stream. The water level is set to produce a dough that sheets cleanly without sticking. Water also activates leavening and hydrates flour. Cocoa powder and flour enter after water, so they are hydrated evenly. Mixing energy is reduced during flour addition to limit gluten development. Excess gluten makes wafers tough and increases shrink during baking. The endpoint is a cohesive dough that is uniform in color with no dry pockets. The dough is then conditioned for forming. Conditioning allows moisture to distribute and lets the dough relax so it does not snap back after sheeting. Dough temperature is held in a narrow band. Warm dough becomes sticky and smears on rollers. Cold dough cracks and produces rough edges. The line uses controlled dwell time and jacketed hoppers to maintain stable dough temperature. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through a series of reduction rollers that gradually thin it. Multiple reduction stages prevent tearing and keep texture uniform. Gauge rollers set the final thickness tightly because thickness controls bake time and final snap. Surface flour dusting can be used sparingly to prevent sticking. Excess dusting is avoided because it burns and creates specks. The sheet enters rotary cutting and embossing. Rotary cutters punch round wafers from the sheet while an embossed pattern is pressed into the surface. The embossing is functional. It controls thickness uniformity, adds texture, and influences how creme bonds. Docking holes are also created during this step. Docking vents steam during baking and prevents blistering. The sheet scrap around the cutouts is lifted and recycled back into the dough stream under controlled ratios. Scrap ratio is limited because repeated working increases gluten and changes dough rheology. Cut wafers transfer to an oven band and enter a tunnel oven. Baking is zoned to set structure and drive moisture to a low endpoint. Early zones melt fat and allow the dough to expand slightly as leavening gases form. Starch gelatinizes and protein set, turning the dough into a porous solid. Mid-zones develop color and drive off moisture. Later zones finish drying so the wafer becomes crisp and stable. Moisture endpoint is critical. If moisture is too high, wafers soften in the package and the sandwich loses snap. If moisture is too low, wafers become brittle and crack during assembly. Oven temperature and airflow are tuned to reach a narrow moisture band. Airflow affects surface drying and color. Strong airflow dries faster and can increase snap. Lower airflow yields a gentler bake and can retain a softer bite. The line controls top and bottom heat to prevent warping and ensure even bake across the wafer. After baking, wafers exit hot and fragile. Cooling stabilizes structure as fats resolidify and moisture equilibrates. Cooling conveyors use controlled airflow. Dehumidified air is often used because crisp wafers can absorb moisture from humid air. Cooling brings wafers to a temperature suitable for creme application. Wafers that are too warm will soften the creme on contact and can cause slip. Wafers that are too cool can be brittle and prone to edge chips. Wafers are sorted and oriented for assembly. Vision systems can reject misshapen wafers and cracked wafers. Thickness checks and color checks verify the oven profile. Good wafers are aligned in lanes, so the embossed side faces the correct direction. Alignment is important because the pattern must be consistent on the outside of the sandwich. Cream. Manufacture runs as a separate stream because it is a fat-based system that must remain stable and non-gritty. The cream is built from sugar, fat, and emulsifiers plus flavor. Sugar is milled or selected to a fine particle size so the cream feels smooth. The fat base is prepared from vegetable fats that are melted and then cooled to a specific plastic state. Plastic state matters because it determines how the cream whips and how it holds shape. Cream mixing begins by blending fat and fine sugar under shear. The mixture transitions from dry and crumbly to smooth as fat coats sugar particles. Emulsifiers are added to reduce viscosity and improve spread. Flavor is added late, so it remains strong. The cream is mixed until particle wetting is complete and the texture is uniform. Air can be incorporated in a controlled way to adjust density. Higher aeration yields a lighter cream that compresses easily. Lower aeration yields a denser cream with firmer bite. Temperature control in the creme is critical. If the creme is too warm, it becomes too fluid and can squeeze out during sandwiching. If it is too cold, it becomes stiff and can crack or fail to adhere. The process holds creme in a narrow temperature range where it is depositable and retains sharp edges after deposition. Cream is delivered to the assembly line through heated or conditioned piping. The depositor meters a precise mass onto each wafer. Depositing is typically done as a spiral or star pattern. The pattern controls spread when the top wafer is applied. The deposit height determines final sandwich thickness. Weight control is tight because it affects bite and package count weight. As soon as cream is deposited, a second wafer is placed on top. Placement systems pick wafers and align them over the cream deposit. The wafers are pressed together with a controlled compression. Compression spreads the cream to the edge without breaking the wafer. Too much compression crushes wafers and causes overspread. Too little compression leaves a tall deposit and weak adhesion. Compression also sets the final wafer to creme contact, which controls stability during transport. After sandwiching, the cookies move through a short setting conveyor. During this stage, the creme fat network stabilizes and holds the sandwich geometry. Cooling can be applied to firm the cream slightly. The goal is a sandwich that can be handled and packed without creme smear. The product is then inspected. Vision checks can detect misaligned wafers and missing cream. Rejects are removed automatically. Packaging is designed to protect wafers from humidity and to protect sandwiches from breakage. Sandwich cookies are stacked into columns and placed into trays. Trays hold stacks in position and reduce movement that would chip edges. The tray is then sealed inside a moisture barrier film. Film barrier performance is critical because wafer crispness depends on low moisture pickup over time. Stacking is controlled, so columns are uniform height. Uniform columns prevent uneven pressure that can break wafers. The stacking system uses lanes and pushers that align cookies without scuffing. Crumb control is important because crumbs in seal areas can compromise seal integrity. The line uses crumb extraction near tray loading and near sealing stations. The tray and film system passes through a heat seal station where the film is sealed to the tray. Seal temperature and dwell are tuned to create a continuous seal without warping the tray. Leaks allow moisture ingress, which softens wafers. Sealed trays are coated and checked by vision. Check weighers confirm pack weight. Sealed trays are then inserted into outer cartons. Cartons are erected and loaded with trays. Cartons add stacking strength and protect the film from puncture. Cartons are closed and glued. Finished cartons are case-packed and palletized. Snickers starts as 3 independent streams that only meet at the assembly belt because nougat, caramel, and chocolate each require different heat histories and different flow behavior to stay consistent at scale. The nougat stream is built around controlled aeration. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level that will support a stable foam once mixed. The cook profile is kept short because long high heat residence darkens sugars and shifts viscosity. The syrup exits the hottest zone and is conditioned to a temperature where it can strengthen a protein foam without scorching it. In parallel, a foaming phase is prepared as a protein solution that can hold fine bubbles. The solution enters a continuous aerator where airflow and shear are controlled to generate a narrow, bubble-sized distribution. Density is measured continuously because density drives bar weight and final bite. If density drifts, the bar becomes heavy and tight. If density drops too far, the nougat becomes fragile and can collapse during cutting. The hot syrup and the foam meet in a continuous mixer designed to fold rather than whip. Folding distributes syrup through the foam while preserving bubble walls. The syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed in small amounts to stabilize the air-fat sugar system and to keep the nougat smooth as it cools. Once the nougat reaches specification, it is deposited as a continuous slab onto a moving belt. A spreader head lays down a uniform band, and gauge rollers set thickness. Thickness control matters because it defines the core cross-section and the later chocolate ratio. The slab enters a cooling tunnel with staged zones that remove heat gradually. Gradual cooling prevents a hard surface skin forming over a warm interior because that skin can crack when the slab is bent or cut. While nougat is being formed, a caramel stream is cooked in parallel. Caramel starts as sugar and glucose, syrup combined with dairy components. The cook concentrates the mix to a solids endpoint that yields elasticity rather than glassiness. If solids are too low, the caramel flows and smears on knives. If solids are too high, the caramel fractures and creates sharp cracks under the chocolate coat. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it remains depositable and stable. Caramel is held in jacketed tanks with gentle agitation to prevent a surface skin. It is delivered to a depositor through heated lines that keep viscosity constant. The depositor is designed to lay down an even sheet rather than a rope. An even sheet is important because Snickers requires predictable bite across the full width of the bar. Peanuts are handled as their own stream because their size and dryness control both crunch and line stability. Roasted peanuts are screened to remove fines and broken fragments that would create dust and weak points. The nut size band is chosen to give a consistent surface coverage without tall peaks. Peaks can pierce the chocolate curtain and create thin spots. Peanuts are cooled after roasting, so residual heat does not soften caramel and does not melt chocolate during enrobing. Assembly begins when the cooled nougat slab reaches the layering station. Caramel is deposited onto the nougat as a continuous layer with a controlled thickness. A leveling bar spreads the caramel and smooths the surface. The temperature of both layers is managed closely. The nougat surface must be firm enough to support caramel without compression. The caramel must be warm enough to bond without sinking into the nougat. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the width with a calibrated feed rate. The nuts land on caramel while it is still tacky, so they adhere. A light compression stage can press nuts into the caramel to improve lock-in. Compression is tuned, so it increases contact without crushing nuts into fragments. The layered slab then enters a conditioning zone. This zone firms the caramel enough for clean cutting and locks nut position. Conditioning is staged to avoid large thermal gradients between nougat and caramel. Large gradients cause differential contraction and can create separation lines. The goal is a slab that behaves as one piece under knives. Edge trimming follows because slab edges often vary in thickness. Rotary knives remove edges and send trim to controlled rework streams. The main slab is then cut into lanes. Lane knives create long ropes of constant width. A crosscutter then cuts the lanes into bar lengths. Knife timing is synchronized with belt speed to maintain tight weight control. Knife surfaces and temperatures are managed because caramel can stick and smear if the blade is too warm or too cold. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between adjacent bars. Transfer points minimize drop height because impact can dislodge nuts and can dent the nougat. A brief pre-chill can be used to firm the bar surfaces. Firmer surfaces improve chocolate coverage and reduce nut movement during curtain contact. Chocolate coating is prepared in a separate system where temper is the critical parameter. Chocolate is melted and filtered to remove unmelted particles. It is tempered in a continuous tempering unit that heats and cools in stages. The process builds stable seed crystals and then sets a working temperature that keeps viscosity steady. Viscosity matters because it defines curtain thickness and therefore coating weight. If viscosity drifts, the bars become heavy or exposed. Enrobing applies chocolate with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a bottoming roller or a bath section that lays a uniform base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the thickness at edges and the foot at the base. Air knife settings are tuned so they remove excess without exposing nuts at corners. If a top pattern is used, a stringer drizzles thin lines across the wet surface. The pattern must be applied while the base coat is still tacky enough to bond. The bars then enter the cooling tunnel immediately, so the coat sets without slumping. Cooling is staged to protect chocolate crystal structure and to prevent cracks around nut peaks. The first zone sets the surface quickly, so the coat holds shape and locks nuts in place. Subsequent zones cool more gradually, so stable crystals grow without stress. Tunnel humidity is controlled to prevent condensation because condensation can create bloom and surface haze. Bars exit at a temperature that supports wrapping without scuffing. During cooling, the internal layers also stabilize. Nougat firms as its fat phase crystallizes and its bubble. Walls become more rigid. Caramel reaches its final elasticity and stops flowing at the interface. The chocolate coat becomes a barrier that slows moisture exchange and protects texture. Inspection follows cooling because surface defects are easier to detect when the coat is fully set. Vision systems check for exposed edges and bald spots and heavy feet. Weight checks verify that cutter control and coating control are stable. Metal detection can be placed before wrapping. Defective bars are diverted to rework. Rework is managed carefully because tempered chocolate cannot be recycled directly into tempered streams without remelting and retempering. Wrapping begins with steady bar spacing into a flow wrapper. Film is formed around each bar and sealed with heat and pressure. Sealed well and temperature are tuned to create strong seals without shrinking film onto the chocolate. Film tension is controlled to prevent scuffing. Code printing is applied for traceability. Wrapped bars can be collated into multi-packs or cartons. Collation uses lanes and gating, so bars group without impact. Cartons are erected and loaded and closed. Finished units are case-packed and palletized. Case patterns reduce movement that can abrade wrappers and stress seals. The industrial strawberry layer cake manufacturing sequence begins at the bulk dry storage terminal. Large-scale suction blowers move sifted pastry flour into the primary weight hoppers. These hoppers utilize load cells to ensure a precision of within 100 grams. A secondary pneumatic line introduces powdered glucose into the flour stream. The glucose prevents the starch from retrograding during the freezing process. Sodium bicarbonate is injected at a ratio of 2 kilograms per metric ton of flour. This leavening agent reacts with acidic components to create the crumb structure. A Z horizontal ribbon blender rotates to achieve a 99% homogeneity rating. The hydration phase starts inside a twin-screw continuous mixing unit. Liquid whole eggs are metered into the chamber at a constant flow rate. These eggs are chilled to 5 degrees Celsius to prevent protein denaturation. A high-pressure pump injects vegetable oil through a series of micro nozzles. The oil coats the flour particles to inhibit excessive gluten development. Deionized water is added to reach a specific gravity of 1.05 for the batter. A jacketed cooling system keeps the mixing chamber at a steady 18 degrees Celsius. This temperature control is vital for the stability of the chemical leavening agents. The aeration stage uses a high-shear rotostator head to incorporate nitrogen gas. Nitrogen provides a finer bubble structure than standard atmospheric air. The resulting batter density is measured by an inline densitometer. This device sends real-time feedback to the gas flow controller. A batter density of 0.45 grams per cubic centimeter is the target for this recipe. The batter travels through stainless steel piping to the manifold depositor. This manifold spans the width of a 1 meter wide steel conveyor belt. Individual piston pumps discharge 60 milliliters of batter into silicone-coated molds. The molds move into a direct gas-fired tunnel oven with 12 independent heat zones. Zone 1 operates at 140 degrees Celsius to facilitate initial lift. The belt speed is calibrated to ensure a 20-minute residence time. Moisture sensors at the midpoint monitor the humidity levels of the oven atmosphere. High humidity prevents the formation of a thick crust on the sponge surface. Zone 6 reaches a peak temperature of 190 degrees Celsius. This heat triggers the caramelization of surface sugars for color development. The final zones gradually reduce the temperature to set the internal cake matrix. Automatic vacuum. Depanners lift the baked sponges from the molds at the oven exit. The sponges are placed onto a modular plastic cooling belt. This belt travels through a HEPA-filtered cooling tunnel for 30 minutes. Ambient air is pulled through the sponges to remove internal heat. The core temperature must reach 22 degrees Celsius before the slicing phase. A battery of reciprocating serrated blades cuts the sponges into 3 equal layers. The blade height is adjusted by microservos based on laser thickness measurements. Each layer is diverted to a separate conveyor for specific ingredient application. The strawberry coulis production wing operates as a closed-loop thermal system. Frozen strawberry blocks are pulverized by a high-torque industrial crusher. The resulting slurry moves into a vacuum evaporator to concentrate the natural sugars. Evaporation occurs at 60 degrees Celsius to preserve the volatile flavor compounds. Liquid pectin is injected into the concentrate to establish a thermoreversible gel. The pH is adjusted to 3.2 using a concentrated lemon juice buffer. This acidity is necessary for the pectin to form a stable molecular network. The coulis is then passed through a fine mesh filter to remove seeds. A plate heat exchanger cools the coulis to 8 degrees Celsius for immediate use. The first applicator station uses a waterfall distributor to coat the base layer. A weight check scale verifies that 40 grams of coulis are applied to each cake. The second sponge layer is placed on top by a high-speed vacuum pick-and-place unit. A second applicator deposits a layer of strawberry-infused cream over the middle sponge. This cream contains stabilized dairy fats and emulsified strawberry solids. The third sponge layer completes the vertical stack before the primary icing phase. The outer frosting is prepared in a pressurized aeration tank for maximum volume. Anhydrous milk fat is blended with sugar syrup and natural stabilizers. The mixture is whipped at 500 revolutions per minute under 3 bars of pressure. This process creates a stable foam with a shelf life of 12 days. The frosting is pumped to a dual-axis robotic icing station. The cake rotates on a pedestal while a side scraper applies the frosting. A top spreader levels the frosting to a thickness of 4 millimeters. Optical cameras inspect the coverage for any gaps or uneven patches. Decorative strawberry rosettes are formed by a multi-nozzle extrusion head. This head uses a star-shaped aperture to create the traditional fluted texture. The extrusion pressure is synchronized with the conveyor belt speed. A secondary station applies a fine mist of pectin glaze over the frosting. This glaze prevents the frosting from drying out during storage. Fresh strawberry quarters are placed into the rosettes by a vision-guided robotic arm. These strawberries are pre-treated with an ascorbic acid wash to prevent browning. A final dusting of pulverized dextrose is applied for visual contrast. The cakes enter a spiral blast freezer for rapid stabilization. Liquid carbon dioxide is sprayed into the chamber to reach -40 degrees Celsius. This rapid cooling creates small ice crystals to preserve the cake texture. The cakes spend 45 minutes inside the spiral freezer. An automated pusher arm moves the frozen cakes toward the packaging line. Cardboard flats are folded into boxes by a mechanical mandrel system. A plastic liner is inserted into each box to prevent moisture loss. The cakes are lowered into the boxes by a soft grip robotic hand. A metal detector scans every boxed cake for potential physical contaminants. This unit can detect ferrous particles as small as 0.5 millimeters. Any rejected boxes are diverted to a secondary inspection bin. A weight grader ensures the final product meets the 500-gram specification. The boxes are sealed with a tamper-evident adhesive strip. An inkjet coder prints the batch number and the production timestamp. The boxes are stacked into corrugated shipping cases by a robotic palletizer. These cases are then wrapped in polyethylene film for structural stability. The palletized goods are moved into the high bay cold storage warehouse. This facility uses an automated storage and retrieval system for inventory management. The temperature is maintained at -18 degrees Celsius with zero fluctuation. Loading docks are equipped with thermal seals to prevent heat ingress during shipping. Every delivery truck is monitored via GPS for real-time temperature tracking. This data is logged into the quality assurance database for compliance. The entire production line can output 800 cakes per hour. This efficiency is achieved through the total integration of mechanical and digital controls. The cleaning in place system cycles through the entire piping network every shift. Hot caustic solution removes fat deposits from the mixing and pumping units. A secondary acid wash neutralizes any mineral scale in the heating elements. The final rinse uses sterilized water to ensure a zero residue environment. All wastewater is treated in an on-site filtration plant before discharge. This plant recovers 90% of the water for non-food industrial use. The factory operates on a 24-hour cycle to maximize equipment utilization. This rigorous process ensures the consistency of the industrial strawberry layer cake. The air quality in the assembly room is monitored for microbial counts. Surface swabs are taken from the conveyor belts every 4 hours. These samples are incubated in the laboratory to check for yeast and mold. The flour silos are equipped with explosion venting panels for safety. Dust collection systems pull fine particles away from the mixing stations. The grease used in the mechanical bearings is food grade certified. All electrical panels are NEMA rated for protection against high pressure washdowns. The facility utilizes LED lighting to reduce heat generation in the cooling zones. The vegetable oil is stored in nitrogen blanketed tanks to prevent oxidation. These tanks are equipped with ultrasonic level sensors for inventory tracking. The sugar syrup is kept in heated vats to prevent crystallization. All raw ingredients are barcoded upon entry for full traceability. This allows the factory to track a single cake back to the specific wheat harvest. The conveyor motors utilize variable frequency drives for precise speed control. These drives reduce energy consumption during periods of lower production. The central control room monitors every motor and sensor in the building. The robotic arms are programmed using a proprietary motion control language. These programs allow for rapid changeovers between different cake sizes. The ultrasonic blades are sharpened using a specialized grinding unit every weekend. This maintenance ensures the cleanest possible cut for the sponge layers. The silicone molds are inspected for surface degradation after every 1,000 cycles. Worn molds are recycled to prevent any silicone migration into the batter. The packaging cardboard is sourced from sustainably managed forests. This commitment to materials ensures the long-term viability of the production model. The industrial fabrication of brownies begins with the high-volume intake of raw commodities. Bulk storage silos hold up to 50 tons of specialized pastry flour. This flour features a low protein content to ensure a tender crumb. Pneumatic transport lines move the flour into the primary sifting station. Vibratory screens remove any particles larger than 200 microns. Cocoa powder arrives in hermetically sealed containers to prevent moisture absorption. This cocoa is typically alkalized to reach a pH level of 7. The alkalization process darkens the powder and mellows the flavor profile. Automatic scales measure the cocoa with an accuracy of 10 grams. A separate line delivers granulated sucrose from a central hopper. The sugar is pulverized into a fine mesh to facilitate rapid melting. Liquid fats are stored in stainless steel vats with internal heating coils. These coils maintain the fat at a constant 45 degrees Celsius. This temperature prevents the lipid chains from crystallizing in the pipes. Refined soybean oil provides the necessary moisture for a fudgy texture. Some formulations utilize anhydrous milk fat for a richer mouthfeel. The primary mixing phase utilizes a high-torque industrial blender. The liquid fats enter the mixing chamber through pressurized nozzles. Cocoa powder is added next to create a thick chocolate paste. This stage is known as the wet rub in the baking industry. The friction from the blades raises the paste temperature slightly. Infrared sensors monitor this heat to prevent scorching of the cocoa. A secondary mixer prepares the hydration base for the batter. Liquid eggs are pumped from refrigerated tanks at 4 degrees Celsius. These eggs undergo inline pasteurization before they reach the blender. A plate heat exchanger flashes the eggs to 60 degrees Celsius. They are immediately cooled back to 10 degrees Celsius. This process eliminates pathogens without coagulating the egg proteins. Natural humectants, like vegetable glycerin, are added to the egg mix. Glycerin binds water molecules to the starch during the baking cycle. This chemical bond prevents the brownie from becoming stale. The dry ingredients meet the wet base in a continuous mixer. The flour is folded in by a twin-screw agitation system. This system prevents the overdevelopment of gluten in the wheat. Excessive gluten would make the brownie tough and bread-like. Salt is injected into the stream at a precise 0.2% ratio. It acts as a flavor enhancer for the chocolate components. A small amount of sodium bicarbonate provides a chemical lift. This leavening agent reacts with the acidic cocoa particles. The batter moves through a series of refining rollers. These rollers reduce the particle size of the sugar and cocoa. A final particle size of 30 microns ensures a smooth mouthfeel. The refined batter is pumped into a vacuum de-aeration tank. This tank removes any trapped air bubbles from the mixing stage. Removing air increases the density of the final brownie slab. A dense structure is required for the fudge classification of the product. The batter reaches a final viscosity of 15,000 centipoise. Industrial brownies often feature inclusions like semi-sweet chocolate chips. These chips are stored in a climate-controlled room at 18 degrees Celsius. This prevents the chips from blooming or sticking together. A vibratory feeder dispenses the chips into the moving batter line. A static mixer folds the inclusions in without shearing them. The ratio of inclusions is usually 10% of total weight. The batter is now ready for the depositing stage. A high-speed manifold spans the width of the production conveyor. This manifold contains 24 individual piston-driven nozzles. The nozzles deposit the batter into large steel baking trays. These trays are coated with a permanent Teflon layer. An automated sprayer applies a secondary film of vegetable oil. The oil ensures a clean release after the cooling phase. Each tray receives exactly 12 kilograms of brownie batter. Optical sensors verify the weight and level of every tray. A mechanical oscillating plate spreads the batter to the corners. This ensures the brownie slab has a uniform thickness of 30 millimeters. The trays enter a multi-zone convection tunnel oven. The oven is 60 meters long to accommodate high-speed production. It is heated by a series of natural gas burners. The first zone is set to 150 degrees Celsius. This initial heat initiates the melting of the sugars. The second zone increases the temperature to 170 degrees Celsius. This is the primary baking phase where the structure sets. Convection fans circulate the air at 5 meters per second. This constant airflow ensures the edges do not burn before the center. Steam injection ports maintain a 40% humidity level. The humidity prevents the top surface from cracking or crusting. The final oven zone facilitates the Maillard reaction. This chemical reaction occurs between the sugars and amino acids. It creates the complex flavor profile associated with baked chocolate. The total residence time in the oven is 28 minutes. An automated arm extracts the hot trays at the oven exit. The trays move onto a modular plastic cooling belt. This belt travels through a spiral cooling tower. Filtered air at 15 degrees Celsius blows across the trays. The cooling process must be gradual to prevent the slab from shrinking. The internal temperature must drop to 25 degrees Celsius. This cooling phase typically lasts for 45 minutes. A vacuum depanner lifts the entire brownie slab from the tray. The slab is placed onto a high-density polyethylene cutting board. This board moves toward the ultrasonic slicing station. Ultrasonic blades vibrate at 20,000 Hz per second. This vibration prevents the dense brownie from sticking to the knife. The blades make vertical and horizontal cuts simultaneously. This creates perfectly square units with sharp edges. The standard size is 5 cm by 5 cm. Any trim from the edges is diverted to a rework bin. This trim is ground up for use in other chocolate products. The individual brownie units are separated by a divergent conveyor. This conveyor increases the space between the brownies for packaging. Some brownies pass through an enrobing station for a chocolate coating. The enrober pours a curtain of tempered chocolate over the units. A blower clears the excess chocolate to maintain a thin layer. The coated brownies enter a secondary cooling tunnel. This tunnel sets the chocolate coating to a high gloss finish. The brownies move into the primary packaging zone. A robotic arm picks up 4 brownies at a time. It places them into a pre-formed plastic blister tray. The tray provides structural support during shipping and handling. A flow wrap machine encapsulates the tray in a polymer film. This film is treated with a nitrogen flush. Nitrogen replaces the oxygen to prevent the oxidation of fats. This gas flushing technique doubles the product's shelf life. The film is heat sealed at both ends by a rotating jaw. A laser printer applies the lot number and expiration date. The individual packs move toward the secondary packaging station. A case packer assembles 24 packs into a corrugated box. This box is sealed with a pressure-sensitive adhesive tape. A check weigher verifies that the case meets the target weight. Any underweight cases are automatically pushed off the line. A palletizing robot stacks the cases onto a wooden pallet. The robot follows a specific pattern to ensure stack stability. A stretch wrap machine secures the load with several layers of plastic. The pallet is tagged with a radio frequency identification label. This label contains the entire production history of that batch. The pallets are moved to a temperature-controlled warehouse. This warehouse is kept at 18 degrees Celsius. Quality control technicians perform a moisture analysis on every batch. They use a halogen moisture analyzer to check for consistency. The target moisture content for a fudge brownie is 12%. A texture analyzer measures the force required to compress the brownie. This ensures the chewiness meets the brand specifications. The cocoa solids are verified using a spectrophotometer. This device measures the light absorbance of the chocolate. The production line operates on a 24-hour schedule. A clean-in-place system sanitizes the mixes between batches. This system uses hot water and biodegradable and detergents. All water used in the plant undergoes reverse osmosis filtration. The factory utilizes a closed-loop energy recovery system. Heat from the ovens is captured to preheat the incoming air. This reduces the carbon footprint of the manufacturing facility. The flour silos are equipped with explosion suppression systems. Fine flour dust can be highly combustible in large volumes. Spark detectors monitor the pneumatic lines for any heat buildup. The packaging room is kept at a positive air pressure. This prevents any dust or insects from entering the clean zone. Workers wear specialized lint-free suits and head coverings. All tools are made from detectable stainless steel. The vegetable oil tanks are nitrogen blanketed to prevent rancidity. Oxygen is the primary enemy of long-term fat stability. The supply chain is tracked using a digital ledger system. Every ingredient can be traced back to its original farm. This level of transparency is standard for industrial food. Production. The brownie recipe is stored in a secure digital vault. The central computer controls every motor and valve in the plant. The automated manufacturing of cheesecake begins with the large-scale processing of the base crust material. bulk quantities of graham flour and wheat flour are combined in a high-speed industrial shredder. This unit pulverizes the baked biscuits into a uniform crumb with a diameter of 2 millimeters. The crumbs are moved via a vibratory conveyor to a horizontal blending drum. Molten butter is injected into the drum through a series of atomizing nozzles. The butter acts as a binding agent to ensure the crust remains structurally sound. Granulated sugar is added to the mixture to facilitate caramelization during the baking stage. The crust mixture is transferred to the primary molding line by a vacuum lift system. Circular spring-form pans move along a specialized belt at a rate of 40 units per minute. A volumetric depositor drops exactly 100 grams of the crumb mixture into each pan. A pneumatic tamping head descends to compress the crumbs with 50 pounds of pressure. This compression creates a dense and level foundation for the cheese filling. The sides of the pans are simultaneously brushed with a light film of release agent. This prevents the cake from adhering to the metal during the cooling phase. The preparation of the cheese filling occurs in a separate, climate-controlled mixing terminal. Industrial-sized blocks of cream cheese are loaded into a vertical, high-shear mixer. These blocks are tempered to exactly 20 degrees Celsius to ensure maximum pliability. A heavy-duty agitation arm breaks the cheese down into a smooth and aerated paste. Liquid sour cream is introduced through a flow-controlled piping network. The sour cream provides the necessary acidity to balance the richness of the fats. Large quantities of liquid whole eggs are then metered into the mixing chamber. These eggs act as the primary emulsifier and structural setting agent for the batter. Pure vanilla extract is injected into the stream via a microdosing pump. The mixing speed is reduced to avoid the over-incorporation of atmospheric air. Excess air in the batter causes the cheesecake to crack during the thermal expansion phase. The batter is monitored by an inline viscometer to ensure it reaches 4,000 centipoise. A final stage of the mixing process involves the addition of cornstarch. The starch binds to the free moisture to prevent the occurrence of syneresis. The finished batter is pumped through insulated stainless steel lines to the depositing station. A multi-piston manifold accurately dispenses the batter over the prepared crust. Each pan is filled to 90% of its total volume to allow for expansion. The pans are then transferred into a continuous water bath tunnel oven. This oven utilizes a shallow pool of circulating water to regulate the heat transfer. The water bath ensures the temperature never exceeds 100 degrees Celsius at the base. This thermal regulation prevents the edges of the cake from cooking faster than the center. The oven is divided into 4 distinct thermal zones for precise moisture control. Zone 1 maintains a high humidity level of 80% to prevent surface drying. The temperature in this initial stage is set to 120 degrees Celsius. Zone 2 increases the heat to 140 degrees Celsius to set the egg proteins. The moisture levels are gradually reduced in Zone 3 to facilitate color development. A light golden hue is achieved on the surface through controlled convection airflows. The final zone utilizes a cooling gradient to stabilize the cake before it exits the oven. The total residence time within the tunnel oven is approximately 90 minutes. An automated arm removes the pans from the water bath at the end of the line. The cakes enter a primary cooling chamber to reduce the internal temperature to 40 degrees Celsius. This slow cooling prevents the cheesecake from pulling away from the sides of the pan too quickly. The pans move into a blast chiller where the temperature is dropped to 4 degrees Celsius. This rapid cooling stage is essential for the final set of the dairy fats. The cheesecake must reach a firm consistency before the depanning process begins. A mechanical depanner uses a series of gentle suction cups to lift the cake from the mold. The springform rings are automatically expanded and retracted for sterilization. The cakes are placed onto a sanitized plastic transport disc for the finishing stage. Many industrial cheesecakes receive a fruit-based topping at this point in the sequence. A secondary manifold applies a layer of fruit puree or glaze to the top surface. The glaze is heated to 60 degrees Celsius to ensure a smooth and glass-like finish. It is immediately cooled by a localized cold air jet to lock the topping in place. If the recipe requires a swirl pattern, a robotic needle system is utilized. The needles inject colored fruit syrups into the wet batter before the baking stage. The robotic arm follows a pre-programmed geometric path to ensure visual consistency. For decorative borders, a multi-nozzle whipping station applies cream cheese frosting. The frosting is extruded through fluted tips to create a traditional rosette pattern. The cakes then move to the high-frequency ultrasonic slicing station. The ultrasonic blades vibrate at 30,000 Hz to prevent the cheese from sticking. This technology allows for perfectly clean cuts through the dense and sticky filling. The machine can slice the cheesecake into 12 or 16 equal wedges. Each wedge is separated by a thin piece of parchment paper to prevent re-adhesion. The parchment paper is fed from a continuous roll and cut by the same blade. The sliced cakes are moved to the primary packaging terminal by a synchronized conveyor. The packaging process involves placing the cake into a rigid plastic dome. This dome protects the decorative frosting and the delicate top glaze. A cardboard base provides structural support and contains the product information. The packages are moved into a vacuum sealing machine to remove excess oxygen. An inert gas flush is sometimes used to maintain the freshness of the dairy components. The sealed units are then placed into individual retail boxes by a pick-and-place robot. These boxes are constructed from high-grade recycled paperboard with a moisture barrier. A laser printer applies the batch code and the specific expiration date to each box. The boxes are grouped into master cases for bulk distribution to wholesalers. Each master case is tracked by a unique radio frequency identification tag. The cases are stacked on pallets by a heavy-duty robotic palletizing arm. The pallets are wrapped in multiple layers of clear stretch film for stability. The finished product is stored in a deep freeze warehouse at -20 degrees Celsius. This freezing stage allows for long-distance transport without compromising the texture. The quality control department monitors the fat content of every batch using a centrifuge. The moisture to solids ratio is checked using a rapid thermal analyzer. Any batch that falls outside of the 5% variance range is rejected. The pH level of the batter is measured to ensure the sour cream has reacted correctly. A texture analyzer probes the center of a sample cake to measure the resistance. This ensures the mouthfeel is consistent across every single production run. The color of the top glaze is verified using a digital spectrophotometer. The industrial facility uses a centralized control system to manage the ingredient flow. Silos are equipped with ultrasonic level sensors to trigger automatic reordering. The water used in the process undergoes a 3-stage purification sequence. This includes carbon filtration and ultraviolet sterilization to ensure purity. The air in the assembly room is filtered through a series of HEPA units. These filters remove nearly all airborne contaminants from the production environment. The floors are sloped to integrated drainage systems for easy cleaning. Every 4 hours, the entire line undergoes a localized sanitation cycle. High-pressure steam is used to clean the depositor nozzles and mixing blades. The conveyor belts are constructed from antimicrobial blue polyurethane material. This material resists the growth of bacteria and is easy to inspect visually. The factory operates on a 24-hour schedule with 3 shifts of workers. The output can reach several thousand units per hour depending on the cake size. This massive scale is necessary to meet the global demand for frozen desserts. The supply of cream cheese is delivered via refrigerated tanker trucks. These tankers are emptied into the holding vats using a pressurized air system. The butter is stored in a separate heated room to maintain a liquid state. All dry ingredients are passed through a metal detector before entering the mixer. This ensures that no foreign objects from the harvesting process remain in the flour. The packaging materials are stored in a dry zone to prevent mold growth. The logistics team coordinates the departure of refrigerated trucks every 6 hours. Ben & Jerry's ice cream is produced by combining dairy and dry ingredients in a multi-stage mixing and freezing process that integrates inclusions and variegates at high precision. The process starts with the batching of the base mix, which is composed of whole milk, cream, liquid sugars, and dry solids such as stabilizers and emulsifiers. Milk and cream are pumped from cold storage tanks into insulated blending vessels. These vessels are jacketed for thermal control and fitted with slow-speed agitators. Liquid sucrose or invert sugar is added next through metered flow lines connected to bulk sugar tanks. Dry components, including milk powder, gore gum, and mono and diglycerides, are introduced through a powder induction system located at the top of the vessel. Powder is drawn into the vortex of the liquid mix through vacuum pressure and blended evenly by the impeller. Once fully blended, the base mix is transferred through sanitary piping to the pasteurization unit. Pasteurization is carried out using a high-temperature, short-time system where the mix is rapidly heated to a fixed temperature above 80 degrees Celsius. The heated mix is held in a thermal chamber for at least 25 seconds and then cooled immediately through a regenerative heat exchanger. This brings the temperature down to 4 degrees Celsius before the mix reaches the aging tanks. Aging tanks are insulated vertical silos equipped with slow-speed agitators to maintain mix homogeneity. The mix is stored here for a minimum of 4 hours and up to 24 hours depending on formulation. During aging, fat crystallization begins and proteins fully hydrate, which improves overrun stability and mouthfeel in the final product. After aging, the cold mix is pumped to the flavoring station. At this point, base flavor ingredients such as vanilla extract, chocolate liquor, or fruit puree are injected inline using precision dosing pumps. Each flavor component is calibrated to match the target formulation and is verified through flow sensors that monitor mass per second. From here, the flavored mix enters the continuous freezer. Continuous freezers are scraped surface heat exchangers that pump the mix through a cold barrel while simultaneously injecting air. The inner barrel surface is chilled using ammonia-based refrigerant and fitted with rotating scraper blades that prevent ice buildup. As the mix travels through the barrel, it begins to freeze on the walls and is continuously scraped into a fine frozen slurry. The injected air creates overrun, which determines the density of the ice cream. Overrun is adjusted by controlling the airflow rate and pump speed and is generally kept below 50% for super premium texture. Frozen mix exits the continuous freezer at a semi-solid state and enters the ingredient feed system. This system consists of a hopper that holds dry inclusions such as cookie chunks, brownie pieces, or chocolate chips. A positive displacement auger pulls inclusions from the hopper and meters them into the ice cream flow at a controlled rate. Each piece is fed in without breaking or melting due to the low product temperature and synchronized speed control. At this stage, variegates such as caramel swirls, fudge ripples, or peanut butter ribbons are also added. These are introduced through a separate pump system that deposits the variegate in a continuous stream alongside the ice cream stream. The product then passes through a laminar blending manifold that gently folds the components together without excessive shear. The structure of swirls is preserved using channelized flow paths that direct streams into the center of the bulk flow. The fully mixed and frozen product is directed to the filling station where pre-formed containers are loaded onto an indexed carousel. Each container is aligned with a filling head that dispenses a measured volume of ice cream. Fill rate is governed by a servo-controlled piston that maintains consistent deposit weight. Once filled, the container advances to a leveling station where a rotating plate smooths the surface of the product. Some variants receive additional toppings at this stage, such as crushed nuts or fudge drizzle, which are dispensed using vibratory feeders or rotary nozzles. Filled containers proceed to lidding, where high-speed arms place and seal plastic lids onto each pint. The lids are pressed down with calibrated force to create a friction seal. The sealed pints then move to the hardening tunnel, which is a spiral freezer maintained at temperatures below -30 degrees Celsius. The product remains in this tunnel for approximately 3 hours to achieve full core hardening. Cold air is forced over the pints at high velocity to extract latent heat uniformly. Upon exiting the hardening tunnel, the pints are conveyed to the coding station where batch information is printed on the lid or bottom using inkjet printers. Following this, the pints enter the cartoning system, where mechanical pushers insert them into printed cartons for multi-pack orders. For single packs, they are collated into crates using pneumatic actuators that align units for stacking. Each crate is conveyed to a palletizing station where robotic arms stack the product according to a programmed matrix. The pallets are then shrink-wrapped and labeled before being transferred to the frozen storage warehouse. Throughout the process, temperatures are continuously monitored and recorded at all key points, including mix tanks, freezers, hoppers, filling heads, and hardening zones. Every production step is automated using programmable logic controllers connected through an industrial network. Sensors measure flow rates, temperature profiles, viscosity, deposit weights, inclusion counts, and air pressure in real time. Adjustments are made automatically to maintain consistency across thousands of units per hour. The mix composition defines final mouthfeel and thermal behavior. Pasteurization ensures phase uniformity and emulsion stability. Aging promotes protein hydration and crystal growth. Freezing governs ice crystal size and air distribution. Inclusion delivery is timed precisely to avoid damage. Variegate folding is optimized for aesthetic and structural preservation. Product texture depends on water content, fat structure, and ice distribution. Overrun level directly affects scoop resistance and volume yield. Inclusion integrity depends on size, shape, and moisture content. Ripple distribution is determined by variegate viscosity and flow channel geometry. Final hardness is a function of exit temperature and hold time in the spiral freezer. Containers are designed to withstand both vacuum during filling and pressure changes during freezing. Lid placement requires precise tolerance to avoid deformation during hardening. Pallet loads are structured to prevent toppling and to allow airflow in the warehouse. All mechanical movements are synchronized to upstream and downstream operations to prevent backup or starvation in the line. Line cleaning occurs between flavor changes using automated clean-in-place systems that flush all internal surfaces with heated detergent followed by sterile rinse. Tanks, pipes, freezers, and filling heads are cleaned without disassembly using pressurized flow circuits. Wastewater is filtered and returned to treatment before discharge. No part of the Ben & Jerry's production process is manual once ingredients are loaded into storage tanks. Ingredient handling, dosing, mixing, heating, cooling, aerating, folding, depositing, sealing, hardening, coding, packaging, and stacking are carried out in a fixed sequence controlled by machine logic. Dairy Queen Soft Serve is created through a multi-phase process that begins with the formulation of a liquid dairy mix. The mix consists of milk solids, cream, sweeteners, stabilizers, and emulsifiers, which are combined in stainless steel batching tanks. The tanks are equipped with slow-speed agitators that maintain uniform suspension of all components during hydration. Milk and cream are pumped from chilled storage tanks using sanitary centrifugal pumps. Sugar is conveyed from bulk hoppers to the mixing tank via auger-fed systems. Stabilizers and emulsifiers such as mono and diglycerides, gargum, and carrageenan are introduced through powder induction ports. The dry ingredients are pulled into the vortex of the circulating liquid using a vacuum venturi system mounted above the mixing tank. The blended mix is agitated until all solids are hydrated and evenly distributed. Temperature in the mixing tank is gradually raised to above 65 degrees Celsius using a jacketed steam heating system. Once the desired blending temperature is reached, the mix is pumped to the pasteurization unit through insulated transfer piping. Pasteurization occurs using a plate heat exchanger which brings the liquid to 80 degrees Celsius or higher for a controlled retention time. After thermal treatment, the mix is cooled immediately to 4 degrees Celsius through countercurrent heat exchange. The chilled liquid is transferred to aging tanks, where it remains under gentle agitation for 8 to 12 hours. During aging, the fat particles begin to partially crystallize, which stabilizes emulsion and improves body and texture. Proteins and gums fully hydrate in this period, which enhances viscosity and mix performance during freezing. The aged mix is then directed to a homogenization unit. Homogenization is performed in 2 stages using a high-pressure valve assembly. In the first stage, fat globules are broken down by hydraulic shear at pressures above 1,500 pounds per square inch. The second stage ensures dispersion of remaining aggregates through pressure equalization at lower intensity. The homogenized mix achieves a uniform fat droplet size, which improves smoothness and prevents creaming. After homogenization, the base mix is cooled again to 4 degrees Celsius and held in refrigerated tanks until needed for production. When ready, the liquid is pumped to filling stations for intermediate packaging or loaded into distribution tanks if sent to retail locations. In stores, the liquid mix is fed directly into soft serve machines, which perform final freezing and aeration. The machines contain a freezing cylinder surrounded by a refrigerant coil. The mix is pulled from the refrigerated hopper into the freezing barrel using an auger system. As the auger rotates, it scrapes the interior barrel surface and simultaneously compresses the mix forward while incorporating air. Air is introduced through a calibrated orifice that meters flow based on pump rate. The ratio of air to mix is tightly controlled to produce the desired overrun, which is typically between 30 and 45%. This ensures a light texture without exceeding melt resistance limits. As the mixture moves through the freezing barrel, it begins to crystallize along the interior surface. Scraper blades continuously remove frozen product and fold it into the flowing stream. The barrel is chilled using a sealed system filled with R404A or similar food-grade refrigerant. The expansion valve regulates evaporator pressure to maintain a barrel wall temperature near -10 degrees Celsius. The partially frozen soft serve exits the cylinder at a semi-solid state with uniform aeration and consistent temperature. The product is dispensed directly from the extrusion nozzle into cones or cups using a gravity-fed or pump-assisted mechanism. Flow rate is controlled by a handle-actuated valve that opens a piston or gate at the nozzle outlet. The nozzle is shaped to produce the distinctive swirl pattern through laminar flow and rotational motion. The final product has a temperature near -6 degrees Celsius and maintains this state for several minutes under normal ambient conditions. No post-processing or hardening occurs after extrusion. Flavor variations are achieved through pre-flavored base mixes or inline syrup dosing. For syrups, a separate pump introduces concentrated flavor into the liquid stream before freezing. Syrup flow is matched to mix rate using flow meters and feedback control. Chocolate-dipped variants are produced by inverting the cone into a vat of liquid coating held at a fixed temperature. The coating solidifies upon contact with the cold, soft-serve surface. The solid layer forms within 2 seconds due to the sharp temperature gradient and the high coconut oil content in the coating formula. Multi-flavor twist products are created using a dual-cylinder system. Each freezing barrel processes a different flavor. Both barrels feed a common extrusion head that contains 2 internal chambers. A Y-shaped nozzle merges the 2 flows at the outlet while maintaining separation. The twist effect is generated by the natural helical movement during downward extrusion. Inclusion-based variants, such as candy or cookie pieces, are added manually at the serving point. Toppings are not incorporated during freezing as they would interfere with scraper operation and pump integrity. Specialty formats, such as Blizzard products, use the same base soft serve dispensed into mixing cups. Solid inclusions are added from bulk hoppers and mixed using a vertical blender with a custom blade. The mixer agitates the entire volume briefly and evenly distributes solid inclusions without altering temperature or structure. The mix used for Dairy Queen soft serve has a fat content near 5% and milk solids non-fat between 11 and 12%. Stabilizers control ice crystal growth during freezing and maintain uniform viscosity during storage. Emulsifiers assist in fat dispersion and reduce weighing during freezing. Overrun is mechanically induced by synchronized air injection and auger transport. Storage tanks are cleaned with automated CIP cycles between production runs. Freezing cylinders are cleaned manually or with clean-in-place systems depending on model configuration. Syrup dosing systems are flushed with warm water after each flavor change. Coating vats are reheated and filtered periodically to maintain viscosity and clarity. All equipment involved in Dairy Queen production is constructed from stainless steel with hygienic welds and polished surfaces. Flow paths are sealed using tri-clamp fittings and silicone gaskets. Pumps use sanitary diaphragms or lobe rotors for gentle handling. Freezing units are maintained at fixed compressor settings based on product load and ambient conditions. The mechanical structure of the soft serve is defined entirely by air cell dispersion, fat matrix stability, and ice crystal size. Each parameter is determined by process inputs such as homogenization pressure, barrel residence time, and freezing surface temperature. No component of the product is batch frozen or aged at the point of service. Every portion is frozen continuously on demand and delivered immediately for consumption. Structural integrity is preserved through shear-controlled mixing and precise overrun regulation. Nestlé ice cream production begins with bulk ingredient staging in temperature-controlled storage silos. Whole milk is held at 4 degrees Celsius in insulated stainless steel tanks fitted with agitators to prevent separation. Cream is stored separately in jacketed vessels and maintained at a consistent viscosity for accurate metering. Granulated sugar is housed in dry ingredient silos connected to the batching system via enclosed auger conveyors. Formulation is initiated by transferring milk and cream to the primary blending tank using positive displacement pumps with flow meters. The tank is jacketed and equipped with high shear agitators that disperse solids efficiently into the liquid phase. Sugar is dispensed from the silo using screw feeders that meter flow by weight. Dry milk solids are pulled into the tank through a Venturi adductor mounted on a recirculation loop. Stabilizers including guar gum and carrageenan are introduced as dry powders via a sealed hopper with rotary valve discharge. Once all components are loaded, the mix is agitated at low speed while steam is applied to the tank jacket to raise temperature to approximately 65 degrees Celsius. This step ensures solubilization of dry materials and begins the hydration of stabilizing agents. When the target temperature and viscosity are achieved, the mix is routed to the pasteurization system through a network of sanitary process piping. Pasteurization is carried out in a plate heat exchanger that subjects the mix to a thermal profile reaching 83 degrees Celsius. Holding occurs in a tubular section sized for 30 seconds residence time at peak temperature. The mix is then immediately cooled to 4 degrees Celsius using a countercurrent flow of chilled water or glycol solution. The cooled mix is sent to a set of aging tanks for further stabilization. Aging tanks are vertical silos fitted with slow-speed agitators to maintain uniformity without air incorporation. Mix resides in the tanks for a minimum of 4 hours and often up to 24 hours, depending on product formulation. During aging, the fat crystals begin to nucleate and proteins reach full hydration, which contributes to improved, overrun, and final texture. Before freezing, the aged mix is pumped through a high-pressure homogenizer that operates in 2 stages. The first stage uses a narrow orifice under 2,000 pounds per square inch to break fat globules into submicron particles. The second stage at reduced pressure eliminates aggregates to produce a fully dispersed emulsion. Homogenization ensures improved creaminess and resistance to fat separation during storage. Flavoring is performed in-line immediately before freezing using precision metering pumps. Flavor oils, cocoa solutions, coffee concentrates, and fruit essences are introduced via multiple injection ports into the flow stream. Flow sensors and control valves maintain exact volumetric dosing. Color additives are similarly introduced where required for specific variants. The flavored mix enters a continuous freezer, which consists of a horizontal, scraped surface heat exchanger. The interior barrel is cooled externally by a closed-loop ammonia system that maintains wall temperature below -25 degrees Celsius. The barrel is fitted with a rotating dasher that scrapes frozen product off the wall while mixing it with incoming liquid. Air is injected through a calibrated orifice located near the inlet, which determines the level of overrun. Overrun in Nestlé ice cream is typically maintained between 40% and 60% depending on the product line. The level of air is controlled by adjusting air pressure, dasher speed, and mix feed rate. Low overrun varieties are set below 40% for premium texture, while novelty products may be aerated to a higher extent for volume efficiency. As freezing proceeds, the product reaches a semi-solid state and exits the freezer through a pump that delivers it to the ingredient blending system. Solid inclusions, such as chocolate chunks, cookie dough pieces, fruit particulates, or caramel bits, are stored in hoppers above the blender. Each inclusion is gravity-fed into a feed auger that meters pieces into the ice cream stream in real time. The blending unit incorporates the inclusions into the flow path using horizontal paddles that avoid crushing fragile components. The feed rate of inclusions is electronically synchronized with the freezer output to maintain uniform distribution. Inclusion size and moisture content are tightly controlled to ensure structural integrity and to prevent bleeding or hardening after freezing. Products that require variegates such as chocolate fudge, caramel, or fruit syrup receive them at a second manifold downstream of the inclusion blender. A peristaltic pump draws variegate from a chilled tank and injects it through a fixed nozzle into the center of the ice cream flow. The pipe downstream is segmented to create controlled turbulence that folds the variegate through the product without mixing it completely. Once all ingredients are combined, the product moves to the filling station through a flexible insulated hose. Depending on the format, the product is filled into cups, tubs, cones, or novelty molds using piston fillers or rotary valves. For cups and tubs, the ice cream is deposited directly into pre-formed containers lined up on an indexing conveyor. Fill volume is precisely managed through a servo-controlled drive connected to the piston stroke length. After filling, surface leveling is performed by mechanical scrapers or rotating wipers depending on the container geometry. Some formats receive additional toppings such as syrup drizzles or solid garnish, which are deposited using vibratory trays or robotic arms. The containers then proceed to the lidding station, where lids are applied using pneumatic cylinders and heat or pressure sealing mechanisms. Filled and sealed units are then transferred into the hardening tunnel, which is a spiral or straight line blast freezer maintained at -35 degrees Celsius or lower. The air velocity within the tunnel is controlled by multiple high-speed fans and directed across the containers in a cross-flow pattern. Residence time in the hardening tunnel varies between 30 minutes and 3 hours, depending on product size and thermal load. During hardening, the unfrozen water content solidifies completely and the overrun structure becomes locked in place. Ice crystal growth is minimized by rapid freezing, which prevents graininess and ensures smooth texture. Hardening is considered complete when core temperature of the product reaches below -18 degrees Celsius. Once hardened, products are ejected from the tunnel and conveyed to the packaging line. For multi-pack items, individual units are collected into groups by mechanical diverters and placed into cartons by robotic pick-and-place systems. Cartons are formed from flat blanks using hot melt glue and folded by rotary formers. Cartons are coated with batch information using thermal inkjet printers. Carton product proceeds to case packing, where cartons are loaded into corrugated cases using side-load or top-load machines. Cases are sealed using tape or glue and labeled with destination and tracking codes. Finished cases are conveyed to automated palletizing stations, where they are stacked using articulated robotic arms onto wood or plastic pallets. Pallet patterns are selected by software based on carton size and unit weight to maximize stability and airflow in cold storage. Stacked pallets are shrink-wrapped with polyethylene film and transferred to blast freezers for holding before distribution. Final storage temperature is maintained at -28 degrees Celsius to -30 degrees Celsius with continuous airflow to prevent warm zones. The entire process from raw ingredient batching to final frozen storage is controlled by distributed PLC systems that communicate over industrial Ethernet. Parameters such as flow rate, temperature, pressure, inclusion count, overrun, and fill weight are monitored in real time. Feedback loops allow self-correction of dosing systems and line speed synchronization. No manual handling occurs at any stage after ingredient delivery. Ingredient silos, mix tanks, pasteurizers, homogenizers, freezers, blenders, fillers, tunnels, conveyors, and packers are all enclosed and automated. Cleaning is performed using clean-in-place systems that circulate caustic, acid, and rinse water through the entire process loop. Each product specification includes parameters for viscosity, Brix value, fat content, solids non-fat, pH, overrun, inclusion percentage, swirl concentration, core temperature, and packaging weight. All values are logged per batch and validated against product standards before release. Nestlé ice cream is defined by tightly regulated thermal transitions, physical dispersion of fat and air, inclusion integrity, and packaging precision. The resulting product has a defined melt curve, scoop resistance, and storage life, which are engineered through material control and mechanical process sequencing. No process stage is isolated or batch dependent beyond the initial mix. All subsequent steps are flow through and occur under continuous conditions to allow high throughput with minimal variation. Formulation changes are implemented by adjusting source tank routing and modifying pump set points. Multiple product lines operate in parallel using shared infrastructure with staggered schedules and automated changeovers. Flavor switching involves purging lines with heated water, followed by air blows and conductance verification before the next product introduction. Nestlé's frozen dessert output relies entirely on integration between thermodynamics, fluid mechanics, solids handling, and process control. Every movement and phase change contributes to the structural and sensory properties of the final packaged unit. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or Sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing, the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. Water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. Proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources such as vegetable oil or butter are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature. because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform, and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix. Salmon production begins immediately after harvesting with rapid transport of whole fish to processing facilities. The fish are received in chilled holding tanks or insulated containers with ice slurry, where temperature is maintained near 0 degrees Celsius to minimize enzymatic activity and microbial growth. Once unloaded, the fish are fed into a de-icing flume system, where circulating chilled water removes surface ice and any external debris. After de-icing, fish are conveyed by stainless steel belt or pneumatic water transport to the grading station. Grading machines use load cell equipped conveyor belts or camera-based systems to categorize each salmon by weight class and body dimensions. Size data is recorded and used to assign each fish to a specific processing line depending on target product specifications. Following grading, salmon are transferred to stunning and bleeding stations. Here, automated percussive or electrical stunning devices render the fish unconscious in under 1 second. Immediately after stunning, a rotary knife or fixed blade system incises the gill arch. The fish then enter a bleeding tank or conveyor where they are held for 5-10 minutes in chilled water to drain blood via circulatory pressure, improving flesh appearance and shelf life. Next is deheading and gutting, where fish are positioned by automated orientation systems to align uniformly before high-speed rotary blades remove the head. The carcasses pass through a ventral incision machine where circular or V blades open the abdominal cavity. Viscera are extracted using vacuum suction nozzles or mechanical scrapers. Internal membranes are further removed by pressurized water jets aimed at the peritoneal cavity. A water flusher system removes residual debris. Eviscerated salmon proceed to the trimming section, where trained operatives or automated vision-guided blades remove the kidney line, dorsal fin remnants, and any remaining membrane tissues. Machine-assisted trimming modules use camera detection and robotic knives for precision cuts at high speed. Visual scanners inspect the cavity for any leftover material. After trimming, fish are re-washed using chilled, potable water from multiple spray nozzles. Washed carcasses are fed into a filleting machine. This equipment uses belt-fed positioning and blade pairs to cut along the spine, separating the two fillets. These blades are height adjusted based on pre-scanned fish dimensions to ensure optimal yield. The resulting fillets are guided into discharge lanes, while frames and collars are diverted to co-product processing. Post-filleting, fillets move to a pin bone removal station. This step is performed using mechanical bone pullers with rotating rubber wheels and suction extraction. The system identifies bone position based on predefined muscle anatomy and removes intermuscular bones without damaging the surrounding flesh. Depending on line setup, bone removal can also be conducted manually with tweezers for premium products. Fillets then pass through trimming belts, where tail tips, belly flaps, collar edges, and skin tears are removed. Trimming can be configured based on customer specification. Camera-based sorting systems ensure uniformity, and deviations trigger diverters to reroute products for manual correction. The next stage is skin removal. Skinning machines feed fillets into a blade interface that separates the skin from muscle while minimizing meat loss. Blade pressure, feed rate, and depth of cut are adjusted via servo control systems. Some processing lines retain the skin for specific markets or product forms. After skinning, fillets are conveyed to portioning systems. Portioning is carried out with water jet cutters, ultrasonic blades, or mechanical slicers. Laser-guided mapping scans the fillet to define weight and shape. Cutting systems then divide the fillet into precise portions according to program parameters, such as fixed weight steaks, loins, or saku blocks. Cut portions are collected in synchronized lanes for immediate packing. In parallel, whole fillet lines bypass the portioning system. These fillets are passed through grading systems based on fat line visibility, color, and size. Multi-sensor units evaluate each fillet with color cameras, near-infrared sensors, and weight scales. Graded fillets are sorted into categories and routed accordingly. Chilling is applied before packaging. Fillets and portions are passed through a spiral or tunnel chiller where they are cooled with cold air or flaked ice mist to reduce core temperature to below 2 degrees Celsius. Chilling units use digital thermostats and humidity sensors to maintain consistent internal environment and airflow. Once chilled, the product enters the packaging zone. Here, fillets and portions are loaded into trays or vacuum pouches. Modified atmosphere packaging is commonly used, where oxygen is displaced and replaced with CO2 and N2 in precise ratios to extend shelf life. Gas mixtures are controlled by flow meters and validated with gas analyzers. Trays are sealed with lidding film using heat sealing units that ensure proper adhesion and headspace control. Vacuum packaged products are loaded into form-fill-seal machines, which mold film around the product, evacuate air, and seal the pack in a continuous motion. Vacuum level, seal time, and film tension are PLC controlled. Pack integrity is tested using pressure decay sensors or inline leak detection systems. After packaging, units proceed to labeling and coding. Print and apply labelers affix product labels with weight, species, origin, and batch codes. Inkjet or laser coders apply best before dates and traceability codes on film or trays. Optical scanners verify label placement and print clarity. Packaged products are then grouped into secondary packaging units. Collating conveyors align packs for insertion into cartons or crates. Case packers load these into pre-formed boxes. Automated box sealers apply tape or glue to secure the cartons. Tertiary barcodes are printed for shipping and scanned for inventory integration. Sealed boxes are routed to palletizing cells. Robotic palletizers stack boxes according to predefined patterns using vacuum heads or fork grippers. Pallets are wrapped with stretch film and labeled with shipment data. Each pallet is scanned and assigned a warehouse location in the inventory management system. Cold chain is maintained throughout with temperature sensors on conveyors, in holding rooms, and inside chilling units. Deviations trigger alerts and system flags. Data is logged and linked to each batch for traceability. End product temperatures are sampled using calibrated probes to verify compliance. Co-product handling operates in parallel. Salmon heads, frames, belly trims, and skin are collected separately. Heads and frames are directed to fish meal or oil extraction. Trimmed bellies may be sorted for smoking or mincing. Skins are graded and can be air-dried or frozen for export. All co-products are processed using stainless steel conveyors, crushers, or mincers with washdown capability. Smoking lines, if present, begin with brining or dry salting. Fillets are conveyed to tumblers or brine tanks, where salt concentrations and immersion time are automated. After salting, fillets are dried in humidity-controlled rooms before entering the smokehouse. Smoke is generated from wood chips or liquid smoke atomizers. Parameters such as smoke density, temperature, and air velocity are digitally controlled. After smoking, fillets are cooled and sliced using parallel slicers calibrated for thickness. In freezing operations, portions or fillets are directed to spiral freezers or contact plate freezers. Products are loaded onto stainless steel belts that pass through cold chambers at -35 degrees Celsius to -45 degrees Celsius. Dwell time is adjusted for product thickness to reach core temperatures below -18 degrees Celsius. Frozen products are bagged and sealed before moving to cold storage. Steak production begins after the animal carcass is chilled post-slaughter. Carcasses are held in cold storage rooms at 0 degrees Celsius to 2 degrees Celsius for 24 to 48 hours to complete rigor mortis and stabilize muscle structure. After this phase, the chilled sides are moved to the fabrication area using overhead rail systems equipped with trolleys. The first step is primal cutting. Sides of beef are placed on breaking tables and cut into primal sections using band saws and large breaking knives. The carcass is separated into forequarter and hindquarter at the 12th and 13th rib. The forequarter includes the chuck, brisket, rib, and plate, while the hindquarter contains the loin, round, and flank. From the hindquarter, the loin primal is isolated, which contains the strip loin, tenderloin, and short loin, common sources for high-grade steak cuts. The rib primal from the forequarter contains the ribeye section. Each primal is weighed, tagged with traceability information, and placed into designated bins or hooks. Primal sections are then moved to the boning line. Here, trained operators or automated knife systems remove bone structures. For ribeye and strip loin, the chine bone, feather bones, and spinal processes are removed using powered wizard knives or mechanical boning blades. Tenderloins are peeled away from the lumbar region with membrane knives, preserving the natural shape and minimizing yield loss. After deboning, cuts proceed to surface trimming, where external fat, silver skin, and connective tissues are removed. Precision trimming is performed using hand tools or vision-guided trim robots. Final trim levels are determined by target specifications, such as 1 4-inch fat cap or lean trim. The trimmed subprimals are transferred to aging rooms or directly to portioning, depending on the program. If aged, subprimals are vacuum packed using thermoforming machines and stored under controlled conditions at 0 degrees Celsius to 2 degrees Celsius for wet aging. Typical wet aging periods range from 14 to 28 days, depending on product line. Aged subprimals are retrieved and conveyed to the portioning area, where they are unpacked and visually inspected. Excess purge is drained, and the product is patted dry if needed to ensure consistency during slicing. Subprimals are loaded onto scanning tables equipped with 3 D-laser or X-ray systems. These systems analyze dimensions, fat distribution, and muscle structure to optimize cutting paths. Based on scan data, subprimals are transferred to automated steak portioning machines. These use rotating circular blades or water jet cutters to slice steaks at consistent thickness and target weight. Blade systems are servo-controlled to adjust angle and pressure in real time, compensating for shape variability. Common cut configurations include ribeye steaks, strip steaks, T-bone, porterhouse, sirloin, filet mignon, and top blade flat iron. Each type is portioned according to thickness specifications, typically ranging from 12 mm to 38 mm, and target weight tolerances within +1%. Cutting yield and number of steaks per subprimal are calculated live by onboard processors. Each steak is then conveyed to a weighing and grading station. Individual steaks pass over in-motion scales to confirm net weight. High-resolution imaging systems evaluate marbling score, surface integrity, and lean color. Grading software assigns visual quality rankings, and steaks are automatically sorted into output lanes based on specification match. Steaks requiring tenderization are routed through mechanical tenderizing machines. These consist of rotating blade rollers that pierce the muscle to sever connective fibers without altering surface appearance. For certain cuts like top round or sirloin, multiple passes may be used to reach the desired tenderness level. At this stage, enhancement or marination systems can be applied. For value-added products, steaks are loaded into vacuum tumblers or injector systems. Vacuum tumblers rotate the meat with liquid solution containing water, phosphate, salt, and flavoring. Injectors use multi-needle heads to evenly distribute brine through muscle fibers at defined pickup rates. Enhanced steaks are rested in staging bins for a defined soak period, then reweighed to verify target pickup has been achieved. Stricter control is maintained for fixed weight packs, where brine gain must fall within narrow tolerances to avoid over or under packaging. From here, steaks are conveyed into the packaging line. For fresh retail presentation, steaks are placed into polystyrene trays with absorbent pads and conveyed under MAP systems. Trays enter a sealing unit where oxygen is displaced with gas mixtures and overwrapped with clear lidding film. For vacuum-sealed steaks, portions are transferred to form-fill-seal machines. In these systems, bottom web film is thermoformed into pockets. Steaks are loaded manually or robotically, and top film is vacuum sealed over the product. Seal bars apply pressure and heat to ensure consistent seal quality. Vacuum sealed steaks, intended for frozen distribution, are routed immediately to spiral or plate freezers. Steaks are individually frozen to core temperatures below 18 degrees Celsius in 30-60 minutes, depending on thickness. Frozen steaks are then bagged or boxed in bulk, with barcode labels applied for inventory tracking. Finished packs pass through metal detection and weight verification systems. Inline metal detectors scan for stainless, ferrous, or non-ferrous contaminants, rejecting non-conforming packs. Check weighers confirm that net weight falls within compliance range. Data is logged to the MES system and linked to batch production ID. Packs are labeled with product name, weight, grade, origin, and expiry using thermal inkjet printers or automatic label applicators. Optical sensors ensure correct label application, alignment, and data accuracy. Invalid or missing labels trigger rejection and pack removal. Labeled steaks are grouped using robotic case packing systems. Retail packs are placed in corrugated shippers or RPCs, arranged according to order profiles. Case formers and glue applicators prepare cartons, which are sealed and labeled with GTIN, lot, and dispatch codes. Cases are moved to palletizing stations, where robotic arms stack them into predefined patterns on wood or plastic pallets. Pallets are then wrapped in stretch film for load stability and scanned into inventory management systems. Each pallet is assigned a location in chilled or frozen storage, depending on product type. All processing zones are monitored with environmental sensors. Temperature, humidity, and air velocity are logged continuously. Conveyor speeds, blade RPMs, cut counts, and yield rates are tracked via PLCs connected to a central SCADA system. Downtime, throughput, and machine error logs are accessible in real time. Quality assurance procedures include destructive sampling and analytical testing. Random steaks are removed and evaluated for marbling score, thickness, weight accuracy, pH, water holding capacity, and sensory characteristics. Steaks are cooked under controlled conditions to assess texture, flavor, uniformity, and juiciness. Chicken strip production begins with the reception of chilled, deboned chicken meat, typically composed of boneless breast fillets. These are transported in bulk containers from upstream slaughter and deboning facilities. On arrival, the meat is inspected for temperature compliance, then tipped into stainless steel hoppers for transfer into the cutting line. Chicken fillets are conveyed to the portioning section, where they are aligned on belts and scanned by high-resolution cameras coupled with laser or X-ray systems. These scanners detect size, shape, and internal structure. Data is processed in real time to guide waterjet or blade-based cutters that slice each fillet into uniform strips based on predefined weight, length, and thickness tolerances. Strips are conveyed into a trimming and inspection zone. Here, off-spec pieces, connective tissue, and surface fat are removed by automated blade systems or manually trimmed depending on the processing setup. A secondary vision system performs quality control on the stripped portions, ejecting defective pieces using pneumatic nozzles. Trimmed strips move into the marination system. The marination line consists of tumbling drums or vacuum massagers. Strips are loaded into the drum, which rotates while marination solution is injected or poured in. Marinade is typically a blend of water, salt, phosphates, modified starches, and flavor compounds. Ingredient mixing tanks feed the drum with chilled solution via peristaltic or centrifugal pumps. Drums operate under partial vacuum or atmospheric pressure depending on marination type. Vacuum assists protein extraction and enhances moisture retention. Tumbling speed and duration are controlled digitally, typically operating at 612 revolutions per minute for 15, 25 minutes. Finished marinated strips are discharged onto dewatering belts to remove excess surface marinade. Moisture-adjusted strips are conveyed into the coating system, a multi-stage line that applies a breading or batter system to each piece. The first stage involves pre-dusting, where strips are evenly coated with dry flour or modified starch powder to improve batter adhesion. Pre-dusting is applied via vibratory sifters and curtain feeders with excess powder removed by air blowers. Coated strips proceed to the battering station, where they pass through a liquid bath consisting of water, wheat flour, leavening agents, gums, and spices. Batter is recirculated continuously through inline filtration and agitation systems to maintain uniform viscosity. Strips are submerged using conveyor paddles, then raised through a vibrating belt to allow excess batter to drip off. Next is the breading application. Strips are dropped into a bed of dry breading mix, which may consist of breadcrumbs, cornmeal, or tempura crumbs. Top and bottom conveyors press breading into the meat surface. Breaders feature reflow systems that recirculate unused coating material after sifting out fines. Compressed air jets remove excess coating. For products requiring double coating, the batter and breading stages are repeated with a secondary set of machines, typically using coarser crumb materials for texture variation. Each station is monitored for line speed, dwell time, batter pickup, and breading adhesion. Strips then enter a setting fryer or pre-fry system. The setting fryer contains oil heated to 180-200 degrees Celsius and is typically 10-30 seconds in duration. This step partially cooks the outer coating to fix structure and prevent loss during freezing. Fryer oil is continuously filtered and circulated to maintain clarity. Exit temperature and surface moisture are measured in line. Post-fry, strips are transferred to a cooling conveyor that uses forced ambient or chilled air to reduce product temperature to under 30 degrees Celsius. Cooling prevents condensation in the next stage and prepares the surface for freezing. Conveyors are made of mesh belts for air penetration. Air velocity and temperature are controlled to stabilize product dimensions. Cooled strips are arranged in rows and conveyed into the freezing tunnel. Spiral or linear IQF freezers are used. Inside the tunnel, product is exposed to high velocity air at temperatures between 35 degrees Celsius and 45 degrees Celsius. Belt speed and airflow are calibrated to bring the product core temperature below 18 degrees Celsius within 15-25 minutes. IQF technology ensures each strip remains separate by using belt vibration, cryogenic burst, or pre-chill alignment. Ice accumulation and belt defrosting are controlled via automated heat pulse cycles. Tunnel freezers are cleaned in place and monitored for temperature uniformity. Once frozen, strips enter the weighing and sorting station. Multi-head weighers mounted above packaging lines portion strips into programmed weight ranges. Optical or X-ray systems recheck for foreign materials, bone fragments, or density anomalies. Rejected product is diverted automatically. Weighed portions drop into bags or trays using form-fill-seal equipment. For pillow bags, film is pulled from rolls, formed into a tube, filled with product, and sealed at the top and bottom by heated jaws. For tray packs, plastic trays are filled and lidded with sealed film using MAP systems, replacing ambient air with nitrogen and carbon dioxide. Each pack is labeled with product ID, batch number, and expiration using inkjet printers or label applicators. Vision systems confirm label placement and code legibility. Weighed packs are verified for target range and conveyed to check weighers. Under or overweight packs are removed via pneumatic rejectors. Packaged units are collated and loaded into cartons. Carton erectors fold and glue cases while robotic arms load a fixed number of bags or trays per box. Cartons are sealed, labeled, and scanned for tracking codes. Logistics data is applied using print and apply labelers that communicate with the plant's ERP system. Boxes are transferred to robotic or gantry-style palletizers. These systems stack cases on wooden or plastic pallets in staggered patterns to optimize height and weight distribution. Pallets are stretch-wrapped using rotary arm or turntable wrappers. Finished pallets are tagged with shipment barcodes and stored in cold storage warehouses maintained at 20 degrees Celsius. All processing stages are monitored by a PLC integrated SCADA system. Control points include marination pump flow, batter viscosity, breading density, fryer oil temperature, freezer airspeed, and packaging line synchronization. Recipe management software ensures every batch conforms to target formulation and processing times. Sensor data is collected from load cells, thermocouples, optical sensors, belt encoders, and pressure gauges. Line operators access live performance dashboards from HMIs to monitor throughput, reject rates, and downtime per station. Alarms and parameter deviations are logged in the plant MES. Quality assurance involves sample testing at key stages. Strip dimensions are measured post-cutting with digital calipers. Batter pickup percentage is calculated by weight differential before and after coating. Oil content is checked using Soxhlet extraction post-fry. Internal temperature is verified post-freeze using calibrated thermometers. Microbial samples are taken from finished product and contact surfaces. Swabs are tested for total plate count, Listeria SPPER, and Salmonella SPP. Moisture, protein, and fat levels are confirmed via NIR spectroscopy or gravimetric methods. Product consistency is tracked against batch specifications. Yield data is compiled for raw input versus packaged output to monitor efficiency. Trimming loss, batter loss, breading recycle rates, and oil usage per kilogram of product are calculated for cost optimization. Rework loops return trimmings and off-spec strips to reprocessing lanes if permitted. Cheetos are produced using a high-output, continuous extrusion system designed for the transformation of dry cornmeal into expanded puffed snacks through controlled heat, pressure, moisture, and mechanical shear. The raw material input begins with degermed cornmeal, which is stored in silos, connected directly to the process line through a network of pneumatic conveyors. The cornmeal is sifted through mesh screens to remove foreign particles, then passed through a dehumidifying chamber to achieve a standardized moisture content between 10.5 and 11.5% before entering the preconditioner. In the preconditioning chamber, dry cornmeal is mixed with water and steam under tightly regulated parameters. The purpose of preconditioning is to hydrate the meal to a target range of 18 to 20% moisture, while partially gelatinizing the starch to prepare it for the extrusion stage. The chamber uses dual shaft paddles rotating at independent speeds to ensure homogeneous hydration without introducing air pockets. Live steam is injected directly through precision steam valves with real-time moisture levels monitored using NIR, near-infrared, sensors and inline conductivity probes. From the preconditioner, the moistened meal is transferred directly into the barrel of the extruder. The extruder is a twin screw or single screw configuration depending on the specific formulation, with segmented barrels for independent control of heating zones. Each zone of the extruder barrel is jacketed and fitted with thermocouples and pressure sensors. The screws inside the extruder rotate at speeds between 300 and 600 RPM and apply intense shear, mixing, and compression to the meal. As the material travels along the screw channel, the combination of mechanical energy and barrel heating increases the temperature of the dough to 140, 180 degrees, while the pressure rises to 1500 to 3000 psi. Under these conditions, the starch within the cornmeal fully gelatinizes and the protein matrix denatures, forming a viscous melt that is cohesive and plastic in behavior. At the final die plate, the pressurized melt exits into atmospheric pressure, causing rapid vaporization of internal moisture. This sudden expansion creates the puffed structure of the Cheeto. The die shape is critical for the form factor of the snack. For classic crunchy Cheetos, the die orifice is a small circular hole, and the dough extrudes as a continuous rope. A rotating knife positioned at the exit face of the die cuts the rope into short, irregular lengths at 200 and 400 cuts per minute, depending on the desired texture. The extruded pieces fall onto a vibrating conveyor belt that transports them into the frying system. For crunchy variants, the base extrudates are fried in a continuous oil bath system. The fryer is filled with vegetable oil, commonly corn or canola oil, maintained at 170 to 190 degrees Celsius, using heat exchangers and recirculation pumps. The extrudates enter on a submerged conveyor belt that keeps them fully immersed for 30 to 45 seconds. During this time, surface water evaporates, and the structure is locked in through rapid dehydration. Oil absorption is measured using inline sensors and confirmed by batch gravimetric analysis. After frying, the product is lifted out of the oil and passes through a cascade of air knives or centrifugal de-oiling drums to remove excess surface oil. The fried product is then conveyed through a multi-stage cooling tunnel where ambient or chilled air flows across vibrating trays to reduce product temperature to under 40 degrees Celsius before seasoning. Airflow is adjusted with dampers to maintain a uniform cooling gradient and avoid moisture migration. For puffed variants, the extrusion process differs at the post-extrusion stage. Instead of frying, the puffed extrudates are conveyed directly into a hot air dryer. The dryer operates at 120 to 160 degrees and includes multiple conveyor decks with perforated trays. Heated air is circulated through the product bed at controlled velocities and relative humidity. Residence time in the dryer ranges from 8 to 12 minutes, depending on piece size and moisture content at exit. Final moisture is targeted at 2 to 3% by weight. After drying or frying, Cheetos pieces are conveyed to the seasoning drum. This is a rotating cylindrical tumbler lined with helical flights to elevate and tumble the product uniformly. The base seasoning is stored in a hopper above the drum and dispensed through a vibratory feeder into a powder application system. Oil-based or water-based slurries are sprayed through atomizing nozzles onto the surface of the snacks as they rotate inside the drum. The seasoning adheres to the surface oil or residual moisture, forming a uniform coating. The slurry composition includes cheese powder, salt, flavor enhancers, colorants, and anti-caking agents. Slurry viscosity is controlled through inline viscometers, and pump speed is adjusted accordingly. Spray coverage is monitored using camera-based imaging systems that detect color uniformity across product samples. Seasoning overuse or underuse is automatically corrected by adjusting feeder rates or nozzle flow. Seasoned snacks are passed through a final cooling stage to ensure surface dryness and coating fixation. Cooled air is circulated over a vibratory conveyor bed, and product temperature is lowered to under 30 °C. The flow rate and cooling length are calibrated to prevent clumping in the packaging stage. Once cooled, the product is conveyed to the weighing and bagging station. Multi-head combination weighers are used to portion the product into precise fill weights, typically between 15 and 300 grams, depending on bag size. Each head drops a known quantity into a central chute when the calculated sum matches the target fill weight. The portioned product is dispensed into pre-formed bags or into a form-fill-seal machine. The vertical form-fill-seal system uses film rolls printed with product branding. The film is fed through a forming collar, sealed longitudinally, and then sealed at the top and bottom to create a pillow pouch. The filled bags pass through a check weigher and metal detector. Packages outside the weight tolerance or those triggering metal detection are automatically ejected via pneumatic arms. Conforming bags are grouped and conveyed to case packing robots. Robotic arms, equipped with vacuum grippers or mechanical paddles, load bags into pre-erected cartons or display-ready trays. Cartons are closed using hot melt adhesive and labeled with product code, batch number, and expiration date, using print and apply labelers. Finished cartons are then conveyed to the palletizer. Palletizing robots stack cartons onto wooden or plastic pallets according to a programmed pattern. Each layer is compressed to improve load stability, and the full pallet is stretch wrapped using a rotary arm wrapper. The pallet is labeled with an SSCC code and barcode linked to the manufacturing execution system. Pallets are transferred to the warehouse and stored under controlled humidity and temperature until distribution. Throughout the process, every production parameter is monitored and logged by a centralized SCADA system. Extruder temperature, pressure, die configuration, screw speed, moisture content, oil temperature, seasoning flow, and packaging weight are all tracked in real time. Automated alerts notify operators of deviations outside process limits. Batch data is stored and used for traceability, yield calculation, and process optimization. Lay's production begins with the intake of bulk potatoes delivered by truck or conveyor into receiving hoppers. Potatoes are unloaded into flume systems filled with recirculating water, which use hydraulic movement to carry them to the first stage of processing. This flume system not only transports the potatoes, but also initiates pre-washing to remove surface soil and debris. Upon exiting the flume, the potatoes enter a rotating drum washer fitted with abrasive surfaces and high-pressure spray nozzles. This drum rotates slowly while jets of water dislodge residual dirt from the potato surface. The wash cycle time is optimized to avoid damaging the skin while ensuring that every tuber is completely clean. The cleaned potatoes are then conveyed to an inspection belt, where optical sorting systems equipped with high-resolution cameras scan for defects such as green skin, rot, or deformities. Non-conforming potatoes are removed by targeted air jets activated in milliseconds. Accepted potatoes are then directed to the peeling stage. Mechanical peelers utilize either steam pressure or abrasive rollers. In steam peeling, potatoes are exposed to high-pressure steam in a sealed vessel for a few seconds, then rapidly released into a vacuum chamber, causing the skin to rupture and loosen. The loosened skin is removed with soft brushes and water sprays. In abrasive peeling, the tubers are rotated inside a drum lined with abrasive surfaces that scrape the skin off while minimizing flesh loss. After peeling, potatoes are rinsed again to remove any residual skin particles. Peeled potatoes are conveyed via stainless steel belts to slicing machines. These are centrifugal slicers equipped with rotating impellers that force each potato against razor-sharp blades mounted on a rotating head. Blade thickness is adjustable down to tenths of a millimeter to produce slices typically between 1.2 and 1.5 millimeter thick. The speed of both the impeller and cutting head is synchronized to maintain consistent thickness regardless of potato size. Slices exit the cutter in a continuous stream and are immediately passed through a water flume to prevent browning caused by enzymatic oxidation. The sliced potatoes are then subjected to blanching. This step involves immersion in hot water or passage through a hot water curtain at 65 to 75 degrees Celsius for 1 to 2 minutes. Blanching reduces starch levels on the surface of the slices, which is necessary for achieving uniform golden color and reducing sugar-related dark spots during frying. It also partially gelatinizes surface starch, which influences final texture. After blanching, the slices are rinsed with cold water and passed over dewatering screens or air knives that remove excess moisture before frying. Next, the slices enter the continuous frying system. The fryer consists of a stainless steel trough filled with vegetable oil, maintained at a temperature between 170 and 190 degrees Celsius, using external heat exchangers and recirculating pumps. The oil is filtered continuously using inline centrifugal or bag filtration systems to remove fines and prevent degradation. Slices are carried through the fryer on a submersion belt that ensures each one is fully immersed for a specific dwell time, usually between 2 and 3 minutes. The exact time and temperature profile is controlled by SCADA systems to produce chips with consistent moisture content below 2%. As the chips exit the fryer, they pass through an oil removal system consisting of vibrating conveyors and high-velocity air blowers or centrifugal de-oiling drums. These reduce surface oil, improving shelf life and texture consistency. The chips are immediately cooled by ambient or chilled air using tunnel coolers that bring the product temperature down below 40 degrees Celsius within 90 seconds. This cooling step also halts cooking and stabilizes texture. After cooling, the chips enter the seasoning system. A vibratory conveyor feeds them into a rotating drum lined with helical flights to provide continuous tumbling. Liquid or powder seasoning is applied via spray bars or auger-fed dosing units mounted above the drum. Liquid flavor systems use oil-based carriers with atomizing nozzles to create fine, even coverage. Powder seasonings are dosed based on real-time weight feedback to maintain precise seasoning ratios. The tumbling action ensures uniform adhesion of the seasoning to the chip surface. From the seasoning drum, chips are transferred via vibrating or belt conveyors to the packaging area. Along the way, they pass through optical inspection systems that detect burnt or misshaped chips using near-infrared cameras and remove them using targeted compressed air pulses. Chips then fall into the radial combination weigher, which consists of multiple buckets that each dispense a known quantity. A computer selects the optimal combination of buckets to match the target fill weight with high accuracy, typically within plus 0.1 grams. Portioned chips are released into the forming tube of a vertical form-fill seal machine. Here, pre-printed film is formed into a tube, sealed longitudinally, and sealed at the bottom to form a pouch. The chips are dropped in, and the top is sealed to complete the package. The seal jaws also cut the film to separate each bag. Each package passes through a check weigher to verify total mass and a metal detector to ensure food safety. Out-of-spec packages are automatically ejected onto a rejection lane. Accepted packages move to high-speed collation and case packing systems. Multiple bags are grouped together using timing belts and dropped into pre-formed cartons or display trays. Automated case sealers close and glue the boxes. A print and apply labeler affixes tracking labels with batch number, expiration date, and barcode. Cartons are conveyed to a robotic palletizer that stacks them according to pre-programmed pallet patterns, optimizing space and transport efficiency. Full pallets are wrapped in stretch film using a rotary arm or turntable wrapper. A barcode, label with product and pallet ID is applied. Pallets are transferred to a climate-controlled warehouse held at consistent temperature and humidity to preserve texture and prevent oil oxidation. All product data, including ingredient lot numbers, frying oil batch, line performance data, and packaging codes are stored in the plant's MES database for full traceability. Throughout the process, ingredient inputs, machine speeds, temperatures, moisture levels, oil quality, and product weights are monitored in real time by integrated control systems. Operators interface with the process through HMI panels, which display alarms, trends, and machine statuses. Recipes are stored digitally and selected at line start to automatically load all relevant parameters across slicing, frying, seasoning, and packaging modules. Cleaning between flavor changeovers involves flushing, slicing, and seasoning systems, draining and filtering oil as needed, and changing packaging film rolls. Flavor specific. Residue is minimized through modular drum systems that can be swapped out quickly and cleaned offline. Line efficiency and waste percentages are recorded for each run and reviewed during shift changeover meetings for continuous improvement. A high-capacity Lay's line is capable of producing between 10 and 15 tons of finished chips per hour, depending on chip type, size, and flavor. Lines can operate for up to 20 hours per day with planned cleaning and maintenance windows. Raw potato usage, slicing yield, oil usage, seasoning consumption, and finished product throughput are tracked and analyzed daily for operational optimization. Doritos are produced using a continuous process that begins with raw corn as the base input. The corn arrives in bulk and is stored in vertical silos with aeration systems to maintain stable moisture content. Each batch is gravity-fed into a cleaning system where the kernels pass through vibrating screens, destiners, and aspiration channels to remove dust, stones, and foreign matter. Magnet separators extract any ferrous contaminants before the corn enters the next stage. The cleaned corn is fed into a steeping tank or continuous cooker where it is exposed to water at temperatures between 80 and 100 °C. The corn remains in this system for 30 to 45 minutes, depending on its initial hardness and desired hydration level. Water is continuously circulated and filtered to remove loosened pericarp, and the corn's internal moisture content rises to around 40 to 45%. Cooked corn is discharged onto dewatering screens and conveyed to the stone mill. The stone mill grinds the wet corn into masa, a soft, pliable dough. The grinding mechanism consists of two rotating stones, one fixed and one rotating, with adjustable spacing to control grind texture. The heat and friction from grinding partially gelatinize the starch. The resulting masa is collected in a trough and transported via auger to the sheeting system. No preservatives or additives are introduced at this stage. Masa is fed into a sheeter system consisting of dual rollers, calibrated to produce a uniform sheet of dough at a thickness between 1.2 and 1.5 millimeters. The sheet is continuously monitored using laser micrometers that provide real-time feedback to the roller gap actuators. The dough sheet moves onto a die-cutting system where rotary cutters stamp out the triangle shape of each Dorito. Scrap masa is collected and returned to the auger to be reblended into fresh dough within a defined recycle ratio. Cut chips move on a perforated conveyor where they are lightly dusted with corn flour to prevent sticking, and then enter a 3-zone oven. The oven zones are independently controlled for temperature and airflow. The chips are partially baked at 300 to 400 °C over a total residence time of 45 to 60 seconds. This reduces surface moisture and creates a semi-rigid structure suitable for frying. The internal moisture content is reduced to around 20% by weight. Partially baked chips exit the oven and are transferred via vibratory conveyors to the continuous fryer. The fryer is filled with high oleic vegetable oil, typically corn or sunflower oil, filtered and recirculated through plate filters to maintain clarity and reduce polar compound formation. Oil temperature is held at 180 to 190 degrees Celsius. Chips enter on a submersion belt and are fried for 50 to 90 seconds, depending on their moisture content and thickness. During frying, final moisture is reduced to less than 2%, and texture is developed through rapid dehydration and surface expansion. Upon exiting the fryer, the chips pass through an oil removal stage. This includes air knives and optionally a centrifugal de-oiling system that rotates baskets at up to 1000 RPM to spin off residual oil. After de-oiling, the chips enter a cooling conveyor system where ambient or chilled air flows across a vibrating bed to bring product temperature below 40 degrees Celsius in under 2 minutes. The cooled chips are then routed into the seasoning drum. This is a horizontal, cylindrical tumbler fitted with internal flights that lift and rotate the chips as they pass through. Seasoning application occurs via two systems: dry powder feeders and liquid slurry sprayers. The dry powder feeder consists of a vibratory tray with variable speed auger dispensing seasoning mix at a calibrated rate. Liquid slurries containing oil-based flavor carriers are sprayed using pressure nozzles fed by gear pumps. Flow rates are adjusted in real time based on chip throughput measured by load cells at the drum's infeed. Seasoning distribution is monitored using optical cameras and hyperspectral imaging to evaluate surface coverage and color uniformity. If discrepancies are detected, feed rates are adjusted automatically. Once seasoned, the chips are conveyed to the packaging section. En route, they pass through inspection systems that identify and reject burnt or broken chips using high-speed cameras and targeted air jets. The accepted chips are transferred to multi-head combination weighers. These weighers consist of multiple hoppers, each holding a portion of chips. A computer algorithm selects the combination of hoppers that adds up closest to the target package weight with minimal deviation. The selected portions are released into a form, fill, seal machine. The packaging film is unwound from rolls and guided through a forming collar, where it is shaped into a tube. The back edge is sealed with a vertical heat sealer, and bottom and top seals are created by horizontal jaws synchronized with the drop of each portion of chips. Packages are filled, sealed, and separated continuously. Each bag passes through a check weigher and metal detector. Non-compliant bags are ejected automatically. Bags are transported to the collation area, where they are grouped into sets for case packing. Robotic arms equipped with suction cups pick multiple bags at once and place them into preformed cartons. Cartons are closed using hot melt adhesive applied by precision nozzles and sealed under pressure. Each box is labeled with batch number, expiration date, and a scannable barcode. Cartons are transferred to palletizing cells. Industrial robots, equipped with vacuum grippers or mechanical paddles, stack cartons in a predetermined pattern onto wooden pallets. Full pallets are wrapped using stretch film applied by a rotating arm or turntable system. A final barcode is applied to each pallet for inventory tracking and scanned into the warehouse management system. Pallets are stored in climate-controlled distribution warehouses maintained at target humidity levels to prevent chip degradation. All critical production data, including ingredient batch numbers, processing parameters, oil usage, seasoning data, packaging film codes, and output weights, are logged automatically by the SCADA system. This data is linked to the finished product batch code and can be retrieved for quality control, traceability, and efficiency analysis. Flavor changes on the production line require equipment cleaning, seasoning drum swap, packaging film change, and system flush. A changeover process is executed based on preloaded digital recipes that configure roller settings, fryer dwell times, seasoning flow rates, and packaging parameters. Downtime for changeovers is minimized using quick-release parts and automated washdown stations. Production lines are modular and scalable. A high-capacity Doritos line can produce between 3 and 7 tons of finished chips per hour, depending on product format. Processing yield is calculated based on raw corn input, fryer oil usage, and seasoning weight compared to bagged product output. Efficiency metrics such as frying oil turnover rate, seasoning coverage variance, and bag fill accuracy are continuously monitored and used for process improvement. Oil management is critical in Doritos production. Fryer oil is circulated through external heat, exchangers, and filtration units that remove carbonized particles and maintain oil quality. Oil is replenished continuously and measured using inline oil meters. Oil turnover is tracked to prevent degradation, which can affect flavor, shelf life, and texture. Used oil is discharged in controlled quantities and either recycled or disposed of based on operational protocols. Seasoning systems support multiple recipe profiles. Each recipe includes component percentages, feed rates, viscosity targets for slurries, spray nozzle pressures, and pump speeds. Recipes are stored digitally and loaded via the line's control interface. Seasoning is prepared in parallel tanks to reduce downtime between batches and allow flavor sequencing. Packaging lines operate at speeds between 60 and 150 bags per minute, depending on bag size and configuration. Packaging materials are stored in automated reels with sensors that alert operators when a roll change is needed. Packaging seal integrity is tested using vacuum or burst testing at specified intervals. Seal strength and print registration are logged alongside product weight and metal detection data. Each Doritos variant, whether original, spicy, lime-flavored, or limited edition, follows the same general processing flow with adjustments made at the seasoning and packaging stages. The ability to scale and shift recipes allows the production line to handle dozens of flavor profiles without hardware changes beyond seasoning and film adjustments.